Hello and welcome to this GCSE chemistry video about pure substances and formulations. We'll start by covering what pure substances are and compare them to mixtures, and then we'll look at how melting point and boiling point are different for pure substances and mixtures, and we'll finish by exploring what formulations are and some examples of how you can be asked about them in a test. Pure substances are taken to be substances which are only made of one type of particle. And it doesn't matter whether this is an element or whether it's a compound. We can have it as being pure if all of the particles are the same. And so in my top example, we've got these atoms that are separated, and this is an element, and all of these particles are the same. And we've got another element at the bottom left, but what we can see is that all of the particles in this box are the same. And so this is a pure element. And we've got another pure element in the top middle. All of the circles are the same colour, all of the particles are the same. And so these are 100% pure because there is only one type of substance. The remaining three examples are compounds, but in each example, all of the compounds are identical. This one at the bottom has got two of the atoms that are shown as being black and one atom shown as being red, but every single one of these compounds are the same. And this one bottom right, all of these compounds have got one black circle and four orange circles. And so that's all the same compound. And on the top right, this compound is pure as well because all of the particles have got one blue atom and one orange atom. And so the compounds are always the same because they're always in the same ratio in each of the examples. So 100% pure, all of the particles are the same. In chemistry then, a pure substance is a single element or a single compound. So pure water is only water. That means it's not been mixed with any other kind of substance. Whereas in day-to-day life, we usually mean something quite different. In everyday language, a pure substance means a substance that has had nothing added to it. So if we get milk straight from a cow and we put it into a bottle, we haven't done anything to that milk to change it in any way, we might refer to that as pure milk. Meaning, though, that it is unadulterated, it's in its natural state. Another example, if we return back to water, spring water or mineral water might be marketed as pure water, but it isn't from a chemistry point of view because it has things dissolved in it. It has minerals dissolved in it, for instance, calcium, magnesium, or sodium, whereas pure water has nothing dissolved in it. Mixtures are different to elements and compounds because they aren't pure. A mixture consists of two or more elements or compounds that are not chemically combined together. And we can show that in particle diagrams. We've got different types of particles that are in the same place and they're shown as not being touching, and that is symbolizing the fact that they are not chemically combined, they aren't bonded together. And you can have mixtures of all sorts of different substances. In the left-hand diagram, we've got a mixture of two different elements in the same place but not chemically combined. In the second example, we've got two different compounds that aren't bonded together, they're just mixed together. And then in the third diagram, we've got an element and a compound mixed in the same place. Some common examples of naturally occurring mixtures are air, which is a mixture predominantly of nitrogen and oxygen, but there are lots of other gases that make up air as well. Seawater is obviously predominantly water, but there are things dissolved in it, for instance, sodium chloride to make it salt water. Rock is actually a mixture of all sorts of different minerals, and soil is a complex mixture of organic matter, minerals, water, and air. The three states of matter are solid, liquid, and gas, and we can use state symbols to represent those terms. We use an S for solid, an L for liquid, and a G for gas. And it's possible to change a substance from being a solid into a liquid, and we call this process melting, but we could also turn a liquid back into a solid, and this is called freezing. A liquid can turn into a gas, and this is called boiling, and a gas can turn back into a liquid, and this is called condensing. The processes of melting and freezing actually both take place at the same temperature, and we refer to this temperature as the melting point. And the boiling and condensing processes also both take place at the same temperature, and we call this temperature the boiling point. Pure substances, whether they are elements or compounds, will melt and boil at specific temperatures. For instance, water. Pure water has a melting point of 0 degrees C, and so that means that if you have a cube of ice, it will melt at exactly 0 degrees C. And water has a boiling point of 100 degrees C, so pure water will always boil at exactly 100 degrees C. This means that at temperatures below 0 degrees C, there isn't enough energy to turn the solid water, the ice, into liquid water, and so water will be a solid at temperatures below 0 degrees C. Once we've reached temperatures above 0 degrees C, there is enough energy to melt the water and turn it into liquid, but it's not yet turned into a gas. But then when we reach a temperature of 100 degrees C, that liquid water can begin boiling and gradually turn into a gas. And so at temperatures hotter than 100 degrees C, water will exist as a gas. Unlike pure substances, which have specific melting points and boiling points, mixtures will usually melt and boil over a range of different temperatures. And so that means they might start boiling at one temperature, but they won't finish boiling until they reach a higher temperature. Or similarly, they might start melting at one temperature, but that substance will not fully have melted until a higher temperature has been reached. In addition to this, the melting point and the boiling point actually changes when compared to the pure substance. And mixtures will normally have a lower melting point than the pure substance and a higher boiling point than that substance. An example of this, if we return back to water, if we add salt to water, this lowers the melting point. And we utilise this when it's cold weather and we are gritting our roads. Grit contains salt, and the salt being added to the water on the roads means that it has to get to a lower temperature before the water changes into ice. And that's because the melting point has been lowered. It also raises the boiling point of water. So if we have a saucepan of pure water, that would boil at 100 degrees C. But if we add some salt to that water, the boiling point will be raised. And so that means that the pan of salty water will boil at a higher temperature, and the food that you're cooking in that saucepan actually gets a little bit hotter. In addition to this, the more salt you add, the lower the melting point gets, and the higher the boiling point will get. And this is to do with the concentration of the salt in that water. A more concentrated salt solution will have a higher boiling point. We can use information about melting points and boiling points in order to distinguish between pure substances and mixtures. And you can be tested on this in an exam in a couple of different ways. Firstly, they might say, how could you find out if a sample of water was pure? And the way that you would do this is you would take your sample and you would heat it and bring it to the boil. So you would boil it. And then whilst you're doing that, you would measure the boiling point with a thermometer. And if it's a pure substance, it will boil at exactly 100 degrees C because that is the boiling point of water. Or they could tell you that a sample of water has a boiling point of 100.6 degrees C. And they could ask you if this was pure, and we can tell by looking at it that it's not, because it's not boiling at 100 degrees C. They might make this more interesting by saying that for each 1% of impurity, the boiling point of water increases by 0.12 degrees C. And you could be asked to calculate the mass of impurity in this water. Well, the temperature has been raised by 0.6 degrees C above the pure water boiling point, and we're told that 1% impurity raises it by 0.12. So we need to find out the percentage impurity by dividing 0.6 by 0.12, and we get 5 there. And so that means that there has been 5% impurity in this water. And so if this sample of water has a mass of 250 grams, we are now in fact just calculating what 5% of 250 grams is. And 5% expressed as a fraction is 5 divided by 100. Then we multiply that by 250 and we get an answer of 12.5 grams of impurity in this water sample. In compounds, the elements always combine in fixed proportions or in a fixed ratio. And you can see that for my middle example where I've got one blue atom and one red atom in every single example of this compound. Unlike compounds, mixtures can be formed in any ratio at all. And you can see that in these three examples at the bottom of the screen. They are all mixtures, and they are all mixtures of the same substances, but each of the mixtures contains the substances in a different ratio, and that's totally possible for mixtures. Any ratio at all is still classed as a mixture. Sometimes we design a mixture in order to use it as a useful product, and this type of mixture is referred to as a formulation. And there are a huge number of examples of formulations, so I will list a few of them here. First of all, food and drink are often formulations, and we add lots of things to foods in order to improve the colour or the taste of something, or perhaps to preserve them, to make them last longer. Other examples include cosmetics, medicines, paint, concrete, fertilizers, alloys. All of these things have been designed in order to perform a particular job. So they are all useful products. They are all formulations. These mixtures that are designed to be a useful product are referred to as formulations because we've made them up to a particular formula or to a particular recipe. And that means that we're using fixed proportions, the same proportions, each time we make up this particular formulation. And this is to ensure that we have consistent properties for our formulations. If we go to a shop to buy our favourite food or drink, we want to get the same experience as the time before when we enjoyed it so much. So it's really important that we have a consistent taste to our food and drink. To use another example of paint, if we wanted to paint the side of our house in green paint, green is of course made from a mixture of blue and yellow that will be in a specific proportion to give us the shade of green that we want to use to paint our house. If we open a second can of paint and it's a different shade of green, then our house will be in two different shades of green. It won't be consistent and we won't have the formulation that we were expecting. In chemistry, you often get asked exam questions that have some elements of maths to them, and formulations is an opportunity for them to test some maths that you haven't learnt before. For instance, it might be that we're tested on percentages or proportions. So for instance, to return to green paint, perhaps this green paint has been made up with 85% yellow and 15% blue. They could simply ask us to express this as a whole number ratio. And when we do this, we have to take our percentages and divide them both by the smallest number, which is 15%. When we divide 15 by 15, we of course get 1. When we divide 85 by 15, we get 5.67 or 5 2/3. This is of course not a whole number ratio, so in order to turn 5 2/3 into whole numbers, we have to multiply it by 3, and when we do that, we get 17. We have to, of course, multiply the blue by 3 as well, so we've got a 17:3 ratio using whole numbers. Or we might be told that burgundy mixture is a formulation used to kill fungi on grapevines, and the mixture is made of two compounds A and B, and the ratio by mass of A to B in this mixture is 1:8. And we could be asked to calculate the mass of A needed in a mixture containing 125 grams of B. Well, there's always 8 times more B than there is A, or perhaps more helpfully, 8 times less A than there is B. And so we need to divide 125 by 8, and we get 15.625 grams, but 15.6 is absolutely fine. One final example, we could be told that a tablet has got a mass of 1.2 grams and it contains 700 milligrams of iron. We might be asked what the percentage by mass of iron is in this tablet. Well, the first thing that we have to do is recognise that our units are not the same for both of the masses. One is in grams and one is in milligrams. We need to convert those so they are both in the same unit. And so I'm going to convert milligrams into grams by dividing by 1000. And that gives me 0.7 grams of iron. Now that, as a percentage, is 0.7 divided by 1.2 multiplied by 100. And that gives me 58.3%. So this tablet is 58.3% iron. Okay, that's the end of this video. Thanks for listening.